All right, Gen Chem kids, we are going to continue on our discussion of isotopes today. Today we are also going to review the 3 subatomic particles that we are wanting you to know that make up the atom: electron, proton, and neutron. We're going to also remind you of where they are located in the atom, their charges, and their relative masses. And the masses we're going to talk about are basically atomic mass units. We're not going to really talk about how much they are in grams. So on this page, this is the next page in your notes from where we left off. I want to create a table over here to just kind of put where or what things are. So create a box on the side here. I want to put protons up here. We'll create a box there. I want to put neutrons here. We'll create a box here, and electrons here. Okay? So the thing that we want to talk about, we want to talk about the location that they have. We want to talk about the relative mass that each of these particles have. And we want to talk about the relative charge that each of these subatomic particles have. So let's take them one by one. So protons, hopefully you've noticed this, protons have that little plus symbol right there. So that should be a hint as to the charge. So protons have a relative charge of +1. Okay? Protons also have a relative mass of 1 atomic mass unit, and they are located in the nucleus. Okay? So they have a mass of 1, they're in the nucleus, and they have a charge of +1. Okay? Our next thing, we're going to talk neutrons. Neutrons with this little 0 here, it means it doesn't have either a positive or a negative. So 0 basically tells us that it has no charge. Or we could say a charge of 0, no charge. It also has a relative mass of 1 atomic mass unit, and it also is found in the nucleus. Okay? Electrons with this little negative sign here, that should give you a hint to the charge. It's a -1. Okay? Electrons essentially are massless. They are about 1 out of 2,000th of an AMU. They're very small. So when we talk about mass, we essentially count this as a mass of 0 because it's so small. And then the location is outside the nucleus. They aren't in the nucleus, but we don't really have a super defined location because the electrons move. They're buzzing all around the outside of the atom. So hopefully this helps you make a little bit of sense. Notice that the particles that have mass are both in the nucleus. And all the charges in the nucleus, positive and 0, are going to also add up to a net positive charge. So we have all the positives in the nucleus, all the mass in the nucleus. And then outside the nucleus, we have all the negatives and very, very little mass. So the nucleus contains the mass and the positives. Outside the nucleus, it's just negative. Okay? So hopefully that helps you understand where things are and the charges and the masses. So let's take a look at this. I have a key here. I want you to put protons next to things that relate to protons, neutrons, or an N, with things that relate to neutrons, and electrons next to things that relate to electrons in these 10 things. Okay, so stop the video really quick, take a minute and do this, and we'll check in just a minute and we'll see how you do. Okay, you guys ready to check? Okay, most of the mass of the atom is in the nucleus. So we need to look what's in the nucleus. In the nucleus, we have both the protons and the neutrons. Okay, a positive 1 charge. Protons have a positive 1 charge. A mass of 1 atomic mass unit. Both the protons and neutrons have that. Makes up the nucleus. Both the protons and neutrons make up the nucleus. Determines the radius, or how far the atom goes outside. What's outside the nucleus? That is the electrons. So the electrons determine the radius of the atom. So if I had something the size of a softball and an atom that was 6 miles wide, that would be the nucleus. Okay, so the protons and the neutrons in the nucleus. So when I put protons and neutrons, I'm really meaning the nucleus. Okay, the nucleus is so small compared to the size of an atom. Most of the atom really is empty space. So we have this little tiny nucleus, and then the electrons are way far away. Okay, 1/2000th of an AMU. That is the mass of an electron. Okay, no charge. Something that has no charge is the neutron. Found outside the nucleus, that is an electron. And a charge of -1, that is also an electron. Hopefully you got these all right. If you did not get them all correct, review a little bit. Okay, so here we're going to fill in this chart for these neutral atoms. Now, neutral means that they don't have any charge. Now, we're going to use the average atomic mass here, and we're going to go to the nearest whole number. Okay? So if I look at, let's grab the nearest whole number for helium really quick. So if I grab the nearest whole number for helium, I have 4. Okay, so I'm going to need a mass of 4 here for, wrong thing that I clicked on. So we're going to need a mass of 4 for helium. Let's look for silicon here. Silicon's nearest whole mass is 28. So we'll put 28 for silicon. Beryllium, let's look here for beryllium. Beryllium's nearest whole mass is 9. So we'll put 9 for beryllium. Hydrogen, the nearest whole mass for hydrogen is 1. So we're going to put 1 for hydrogen. Radon, let's look for radon. So radon's nearest whole mass is right here, 222. Argon, you find it. Argon's nearest whole mass is 39.9. So whole number would be 40. It would round to 40. So we're going to put 40 here. Fluorine, our nearest whole mass for fluorine is 18.998. So that whole number is going to round to 19. And lead. Lead's the last mass that we need to grab. So lead is right here. Nearest whole mass is 207. So here we go, 207. Okay. Now, the other thing that we need to grab from the periodic table is protons. And I probably should have grabbed them. I'm going to, let's just grab it from the periodic table really quick. So I should have grabbed these before. Helium is 2. So we're going to look at this bottom number now. 2 for protons for helium, 1 for hydrogen, 4 for beryllium, and 14 and 9. Let's see if we can remember those. 1, 2, 4, 9, and 14. So protons for helium, 2, hydrogen, 1, fluorine was 9, right? And then we had silicon, which was 14. We have a few more to look up. So beryllium and radon and lead. So beryllium we had 4. Argon we had 18. So 4 for beryllium, 18 for argon, 82 and 86. Okay, so let's see if we can remember those. 4, 18, 82, 86. So 4 and 18, 82, and 86. And that's a horrible 8. $86. Okay, so we're set. Now we can finally figure out mass and protons, neutrons, and electrons. So we've already figured out the mass, and we should do the notations here with that little line. So the mass is the protons plus the neutrons. So mass, we're just going to copy the numbers that we put with these dashes here, because that is the mass of these elements, these isotopes of these elements, I should say. Remember, protons plus neutrons equals the mass. So if I have my mass and I have my protons, can I just take my mass minus my protons to get my neutrons? I definitely can. So 4 minus 2 will give me 2 neutrons here for helium. And remember, protons, for neutral atoms, protons are going to equal electrons. So 2 right there. Okay? So 28, our mass for silicon, minus our 14 protons will give me 14 neutrons. Remember, protons on a neutral atom equal electrons, so I will have 14 electrons. Okay, beryllium, 9 minus 4 will give me 5 neutrons. And 4 protons have to be balanced with 4 electrons. Okay, how are you doing here? Mass of 1 minus 1 gives me 0 neutrons. 1 proton, 1 electron. Okay, this one I'm probably going to want my calculator here. So radon, I have 222 minus 86 to get me my neutrons. So that will give me 136 neutrons. And then if I have 86 protons right here, I'm also, for a neutral atom, I'm going to have 86 electrons. Okay, my mass number, 40 minus 18 to get me my neutrons. So 40 minus 18 will give me 22 neutrons. If I have 18 protons, I'm going to also have 18 electrons. My mass for fluorine of 19. 19 minus 9 will give me 10 neutrons. If I have 9 protons, I'm also going to have 9 electrons. And this one, I'm going to also want to do my calculator. 207 minus 82. So the mass of 207 minus 82 will give me my neutrons of 125 neutrons in an atom of lead. And if I have 82 protons, I'm also going to need 82 electrons so that we balance those charges and have a neutral atom. Okay, hopefully that made sense. If you want to watch that again, you can. Okay, average atomic mass. Now notice we have lots of isotopes here. Lead has many, many isotopes. Not all of them are 207. So if we look at lead, the average atomic mass on that periodic table is 207.2. Where does that 0.2 come from? I had it as 207. It's because not all lead is 207. We have lead that's 209, we have lead that's 210, and lead that's 211. So we have lots of different isotopes. So that's where we get these numbers with the decimals from the periodic table. That is our average atomic mass. So it's kind of like if I give you guys a quiz or a test, does every student get the same score? No. I can get a class average, but it doesn't mean that every kid in that class scores that same score. So these masses that we see on the periodic table, let me get here, on this periodic table, these masses, notice that we have decimal places on a lot of these. That's because we're averaging out all the different isotopes. Okay, so let's learn how we calculate that really quickly. Okay, do all the atoms of the same element have the same mass? No, we have isotopes. No, there are isotopes. So they have the same number of protons, but different number of neutrons. Okay, so that means they have different mass because neutrons also weigh something. Okay, so let's do a little thought experiment here. If I wanted to take the average weight of a student in my class, how would I do that? Now, most of you would say I would take the weight of every kid and I would add it up, and then I would divide by the number of students. And that is how we'd find an average. Well, let's think about it here on this thing. This is a thought experiment. What would be the average weight of a student if 20 of you weighed 100 pounds and 10 of you weighed 200 pounds? How would I take that average? Would I just go 100 plus 200? That gives me 300 divided by 2 because I have two different masses or weights and the average is 150. Would that work? No, that would not work because I have more kids weighing in at 100 pounds. So I have to weigh the 100 pounds more than I have kids weighing in at 200 pounds. So I've got to do what I call a weighted average. So this is how I would do it. I would do this. I would have 20 multiplied by 100 for the 20 students that are weighing in at 100, plus I would add 10 multiplied by 200 for those of you who are weighing in at 200 pounds. And then I would take all of that. And how many students do I have total? 20 plus 10 is 30. So I would divide it by 30 to get the average. So if I do that, 20 times 100 plus 10 times 200 is 400. So I would take 400 divided by 30. And I would get or it's 4,000, sorry. It's 4,000. I would get 133.3 repeating pounds on average. That would be my average. X bar means average or mean. The mean. Remember when you do mean, median, mode? So when we do average, we're really meaning the mean of the data. Okay? So it's the same way that we would do it for atoms of the same element. We would take what we call a weighted average. I would have to take into account how much of that element comes from this isotope versus that isotope. Okay? So let's do a practice. Calculation of the average atomic mass. The element boron exists in two isotopes. So I have boron 10 and I have boron 11. The boron 10 consists of 5 protons and 5 neutrons, right? Protons plus neutrons will equal the mass. So 5 plus 5 equals 10. That's what we would expect. The other has 6 neutrons and has 5 protons. Remember, proton number has to stay the same, because if the proton number does not stay the same, it's no longer boron. Okay, so it's going to be 5 protons and 6 neutrons to add up to 11 for that mass of 11. They exist in nature. Boron 10 is 20%, and boron 11 is 80%. So how am I going to calculate that average mass? So the masses are 10 and 11 AMU respectively. So boron 10 is 10, boron 11 is 11. So I'm going to do something that you probably haven't done for quite a while. I'm going to take these percentages and I'm going to make them decimals. Okay, or in other words, I'm going to make them probabilities. I'm going to make them decimals. So 20% as a decimal is really 0.20, right? And 80% as a decimal is really 0.80. Do you guys agree with that? Then I also need to multiply the masses that they are associated with. So the 20% is associated with boron 10, which is 10 mass, a mass of 10. And the 80% is associated with the 11 AMU. I'm going to add those up. And when I add those up, I'm going to get an average mass. So let's do this piece by piece. 0.2 times 10 will give me 2. And then 0.8 times 11 will give me 8.8. So when I add 2 plus 8.8, I will get 10.8 atomic mass units. This will be my average mass of boron. Okay? So if I look on the periodic table, should we see how close we get? Let's look. So if I look at boron, oh my. It's not going to let me look at boron. It is about 10.2. So I do come really close. All right. So let's go on to our next thing. Why are atomic masses listed on the periodic table not whole numbers? I already talked about it a little bit ago. Do you remember why? Write it down. See if you remember why. Once you're done writing it down, we'll check it. Okay. Did you write it down? So, atomic masses listed on the periodic table are not whole numbers because they are the weighted average They're the weighted average of all the isotopes of that element. Okay, so you're never going to really land on a completely whole number when you're doing a weighted average of all the elements isotopes. There are isotopes for every single element out there. Okay, let's do some more. Okay, actually, no, I think we're done for today. Yep, that is it. So next time, as you can see, we're going to be doing some nuclear chemistry. So we're going to be closing up this unit and starting on nuclear chemistry starting next week. So enjoy. We'll talk to you later. Bye.